Welcome to the audio version of Lightning Meteorology 2, Anomalous Storms in Advanced Theory. This session was developed by Bard Zajac and John Weaver. My name is Dan Lindsay. I will be presenting it today along with John Weaver. The broad objective of Lightning Meteorology 2 is to utilize CG lightning data in storms that are anomalous when compared to the typical warm season storms that we talked about in Lightning Melt 1. To meet this objective, we first distinguish between what we mean by typical and anomalous storms, and then we introduce theory on electrification, charge distributions, and CG lightning production. And then finally, we present some research results and some AWIPS case studies which demonstrate consistency between theory and observation. One thing to keep in mind is that the theory discussed here in Lightning Meteorology 2 is much less refined than the theory from Lightning Meteorology 1. Most of this lies at or near the boundary of research knowledge, and some of the results are from papers which have come out in the last couple of years and may not be completely accepted in the entire electrification and meteorological communities. The objectives of the course are to define the two main CG lightning parameters, the CG flash rate and the percent positive CGs, and talk about some factors which control these two parameters. Secondly, we'll want to be familiar with negative strike dominated or NSD and positive strike dominated or PSD definitions. Third, we want to identify differences between warm and cold season lightning and talk about some factors which may be responsible for these differences. Next, we want to see why severe NSD storms may exhibit unusually high and variable cloud-to-ground flash rates. And finally, we want to be familiar with the true anomalous storms, severe PSD storms, and talk about some hypotheses used to explain why these storms exist. Section 1 will be a brief review of Lightning Meteorology 1. Section 2 will talk about the lightning parameters and discuss the NSD and PSD definitions. Section 3 will be cold season lightning, and we'll look at 5 short examples. Section 4 will discuss severe NSD storms and look at a case study from Birmingham, Alabama from 8 April of '98. And finally, Section 5 will talk about severe PSD storms and look at a couple of case studies, the first from North Platte, Nebraska, and the second from Norman, Oklahoma. The objective of the first section is to review Lightning Meteorology 1, which examines typical warm season storms. We'll talk about electrification, charge distributions, and the CG lightning production that we expect in the typical warm season isolated storms and mesoscale convective systems. Shown here is the charge structure that we expect within a typical isolated summer thunderstorm. This figure represents the gross charge distribution, and what you can see is that we have a predominantly large area of negative charge here located between about 0 degrees Celsius and about maybe minus 20 degrees Celsius. This negative charge is associated with grapple particles which have formed and grown by riming and collided with the smaller ice crystals within this very high cloud liquid water portion of the storm. Within a high cloud liquid water content area, whenever grapple collides with ice crystals, the grapple takes on a negative charge and the ice crystals take on a positive charge. The smaller, lighter ice crystals are then advected upwards into the storm, and so therefore we have predominantly positive charge located here in the upper portion of the storm. The other charge region that we see is down here just below the melting level near the 0 degree Celsius isotherm. This positive charge region has shown to exist, but it's not really understood very well why it does exist there. Another thing to point out here is that since we have a large area of negative charge in the middle portion of the cloud, we see some positive charge which is induced on the surface below, and this aids in the actual discharge process. As the mature cumulonimbus cloud dissipates, the positive charges located in the anvil are advected further down into the anvil in this region. The grapple particles that were located at mid-levels have mostly either melted or fallen out of the storm, but we do see some negative charge which still does exist within the middle portion. And we still see a couple of positive charges here located around the melting level. So what type of CG lightning do we expect within the typical warm season storm? Well, we expect negative CGs within the convective core. These would be electrical strikes which the discharge begins here between the negative and positive charge, and negative leaders extend downward and eventually reach the surface, and we call this a negative CG because it's a negative leader extending downward. We would expect positive CGs mostly from the upper levels. That would be from possibly this portion of the cloud, possibly the anvil portion of the cloud over here. As far as total numbers, we would see a much larger number of negative CGs from the convective core than positive CGs. In Lightning Met 1, we did a case study from Melbourne, Florida on 28 June of 2000, and this figure shows a 6-panel radar loop, basically, with a CG lightning overlaid. Some storms have formed along the sea breeze front west of the Melbourne area here around 1934Z, and at the beginning you can see some cores developing but no CG lightning production. By 1939Z, we begin to see the first CG lightning strikes, which indicate that graupel has formed, charge separation has occurred, and we begin to see some electrical discharge within the cloud. That continues through 1944Z. By 1950Z, notice that we see the first positive strike occurring down here to the southwest of the storm, seemingly out of nowhere. Well, it turns out that this is actually an anvil strike. The upper-level winds, the anvil-level winds, were out of the northeast on this particular day. And if you notice as we go in time, we begin to see some stratiform rain falling out of the anvil. By 2001Z, the lightning activity, or at least the CG lightning activity, has stopped altogether, telling us that the graupel has probably either melted or fallen out, and that the storm is probably going to be dissipating beyond this point. Shown here is the charge structure that we expect within a mesoscale convective system. The MCS charge distributions are best divided into the convective and stratiform regions. The convective regions, which we would say are located in this portion of the MCS, are very similar to isolated storms because we have negative charge located here at mid-levels and predominantly positive charge above, with a little bit of positive charge located near the melting level. This is again a high cloud liquid water environment, and that's why we get these negatively charged graupel particles. Within the stratiform region of the MCS, we have a much more complex picture of the charge structure. We have a much lower cloud liquid water content and predominantly aggregated ice particles rather than graupel. As these aggregates, which have collected some rime, collide with the smaller ice crystals, the aggregates actually take on a positive charge, and the ice crystals take on a negative charge. So this portion of the cloud that I'm circling now is primarily associated with these positively charged aggregate particles, and also possibly some advection of charge from the stratiform region. The negative charge area located below that is again associated with a melting level, and this is a region which is shown to exist, but not many people really know, or really no one knows why it exists, but it's important for the discharge process. So what about the CGs we would expect? Well, within the convective core, just as was the case with the isolated storms, we expect mostly negative CGs. Why? Well, it's because we have this large area of negatively charged graupel located at this area, and the discharge process will begin just below that, and therefore negative CGs. Again, we expect positive CGs within the forward anvil because we have predominantly positively charged ice particles up here in the forward anvil. And we would expect positive CGs within the stratiform area of the MCS. Because of this large area of positive charge located here, we would get a positive leader which extends downward toward the negative charge and toward the negative charge which is induced on the surface, and therefore we would expect a positive CG. As far as the flash rates go, again, the flash rate within the convective core is going to be lots higher, primarily because we have such a large density of these negatively charged graupel particles there. In Lightning Meteorology 1, we talked about another case study from Des Moines, Iowa on 29 June of '98. It was a severe MCS moving through central Iowa, and shown here is the radar at a particular time, and now I'm going to toggle on the CG lightning, and you can see several interesting things from this. First, the very large density of negative CGs are clustered within the highest precipitation, within where the radar has the highest DBZ values. That tells us, it sort of confirms our suspicions that negative CGs are indeed associated with the convective cores. Also, up here to the northeast of the core, you can see some positive strikes which are indeed associated with the stratiform region of the MCS. And finally, out here ahead of the MCS, we see positive strikes which are most likely associated with the forward anvil of the storm. Now, if the radar goes away, which is actually what happened in this case around 1915Z, as a forecaster, we would have to look at something different in order to issue warnings and forecasts. This is an example of what we could look at. This is infrared satellite imagery with the CG lightning overlaid. I'll concentrate on the times after 1915Z because that's when we did indeed lose the radar data. Notice that we still have this very large cluster of negative CGs. We can infer that that's associated with the heaviest rainfall in the convective core. By 2015Z, notice how these negative CGs have begun to bow outward, and especially that's the case at 2045Z. So you can infer that the reflectivity values are probably bowing outward as well, and that there's very likely some high winds associated with this MCS. And indeed, there was quite a bit of severe wind damage in southeastern Iowa, as well as this thing moved into Illinois on this particular day. There was a wind gust of 126 miles per hour in the town of Washington in southeastern Iowa. So this is just an example of how CG lightning can be used in addition to other products that you have to issue warnings or to supplement or maybe replace radar data if it goes away. In summary, you should be familiar with the following terms or concepts from Lightning Meteorology 1. Ice-ice or grapple-to-ice collisional charging, cloud liquid water, charge generation and advection, induced charge at the surface, and most importantly, the expected location and frequency of negative and positive CGs within isolated warm season thunderstorms as well as MCSs. Moving on now to Section 2. The objective here is to define the two main CG lightning parameters and talk about some factors which control these parameters. The first is the CG flash rate, which we'll call FR, and the second is the percent positive CGs, which we'll call percent P. We'll talk about the factors which control these and look at some examples in AWIPs. The second objective here is to clarify the definitions of negative strike dominated or NSD and positive strike dominated or PSD. The CG flash rate is defined in several different ways. The first is called the CG flash count, and that's simply the number of CGs over a specific time and area. Overall, this is really not all that useful of a parameter. The more useful parameter to me is the CG flash rate, and that's defined as the number of CGs per unit time over a specific area. The unit here would be strikes per minute, or basically strikes per some amount of time, maybe 15 minutes or hour or something like that. And this is a product that you actually do have in AWIPS, and you can pull up and decide whether you want to look at 5-minute flash rate, 15-minute flash rate, hourly flash rate, or whatever. And then the final one is the CG flash density, and that's simply the number of CGs per unit time and area. And the unit here would be number of strikes per area per unit time, so maybe per square kilometer per minute. And this is useful when you're looking at an area of a storm which is producing lots and lots of lightning over a very short amount of time. The percent positive CGs are defined in a different way. We have the percent positive CGs, it would be the total number of positive CGs divided by the total number of all CGs. So it's defined exactly the way you would expect. The flash rate for negative CGs and positive CGs depends on three main factors: the charge density, the distance between the charge and the surface, and the amount of shielding by the opposite charge. So, for example, if we wanted to increase the flash rate for negative CGs, we can do that in three different ways. We could first increase the density of negative charge. That would be like forming more grapple and basically having more and more collisions, and therefore allowing the better chance of seeing some negative CGs. We could decrease the distance between the negative charge and the surface. That would allow for the discharge process to occur more readily. Or we could decrease the shielding by positive charge. That means we could make the positive charge located below the negative charge smaller in density, and therefore the negative charge should do a better job of actually discharging as well as inducing some charge at the surface. This plot is a 15-minute time series of CG lightning over the Gulf Coast of Florida averaged over the warm seasons, June through August of 95 to 99. What we're looking at on the x-axis is the hour in local time as we go through one day, and the relative frequency of negative charge in black and positive charge in red. The pink line is the percent positive CGs. What we see here is that the relative frequency of both negative and positive CGs begins to increase around 10 a.m., which is when storms begin to form. Throughout most of the day, as the storms are building, the negative charge, indicated by the black line, the relative frequency of negative strikes, indicated with the black line, is greater than the relative frequency of the positive strikes, indicated by the red line. And this is because the storms are forming, and we have predominantly grapple particles at mid-levels, and therefore mostly negative CGs. As the storms begin to dissipate, this trend switches over, and we see that relative frequency of positive CGs increasing and going greater than the relative frequency of negative CGs. And this is due to the fact that there's lots of these positively charged ice crystals which are advected into the anvil portion of the cloud, and we see more strikes from the upper levels, most of which are positive. Also, lots of the grapple has melted or fallen out, so the frequency of negative CGs goes down. At the same time, the pink line, which is the percent positive CGs, goes down to a minimum here around noontime when the storms are building and begins to increase again late in the day as the storms begin to dissipate. Knapp in '94 coined the terms negative strike dominated or NSD and positive strike dominated or PSD in a severe weather CG lightning study. He gave NSD and PSD fairly narrow definitions for use in specific scenarios. We, on the other hand, are going to offer more general definitions. An NSD storm will be defined as a storm which the percent negative CGs are greater than 50% within the storm's core for a significant portion of the storm's life. A PSD storm is a storm where the percent positive CGs is greater than 50% within the storm's core for a significant portion of the storm's life. The following statements explain our usage of NSD and PSD. First, typical warm season storms are negative strike dominated throughout their life cycle, except for dissipation when they sometimes transition over to PSD. In most warm season MCSs, convective regions are NSD, while the anvil and stratiform regions are PSD. And storms dominated by positive CGs during a significant part of the mature phase are called PSD storms, even though they may be negative strike dominated for a portion of their lifetime. Summarizing Section 2, we defined the two main lightning parameters, the CG flash rate and the percent positive CGs. We also talked about the controlling factors, the density of charge, the distance between the charge and the surface, and the amount of shielding by the opposite charge. And finally, we discussed and defined NSD and PSD. Now at this time, I'm going to turn it over to John Weaver, and he's going to talk about cold season lightning.
Now we're going to begin talking about the first major category of CG lightning, whose behavior differs appreciably from the typical warm season convection that we focused on during all of Lightning Meteorology 1 in the first part of this session. This will be cold season convection. We're going to look at CG flash density and the percentage of positive CGs, comparing the two seasons. We're going to look at 5 AWIPS examples to show that that some of these characteristics during the cold season happen over most of the continental United States. And then we're going to talk about factors that affect the percentage of positive CGs that occur warm season versus cold. This graph has a lot of information on it, but it does show the most important differences between warm and cold season lightning. The solid blue area here represents the mean daily flash count averaged over the continental United States for the 5-year period, 1995 through 99. This is from a study by Bart Zajac and Steve Rutledge. We've arbitrarily defined the warm season to run from April through September, and the remaining months are cold season months. The most obvious thing that catches your attention immediately is the large number of the large amount of CG activity during the warm season as compared with the cold. But another important difference is shown by the line that's giving us the percentage of those cloud-to-ground strikes that are positive counts. That's this line right here. Notice that during the cold season, that positive line as a percentage of the total is above 15%, and as we go into the warm season, it drops way down. These cases shown here are from Lightning Meteorology 1, showing the percentage of the strikes that were positive strikes for the 4 case studies that were in Lightning Meteorology 1. These are results again from Zajac and Rutledge, a study they did 2001. In 2001, covers the years 1995 through 1999. It shows the percent positive CGs, or the percentage of the cloud-to-ground strikes that were positive for the continental United States. We've added a little fiducial mark here that represents a moderately high lightning flash rate in terms of the average. You can see that for most of the continental United States, we get a reasonable amount of lightning, and for most of the continental United States, the percentage of positive CGs as a percentage of the total is less than 15%. In fact, for a lot of the country, it's less than 10%. and here's a large area where it's less than 5. Now, if we look at the winter season, that's the months October and then across the winter through March, we see that the area that has a reasonable strike density has shrunk up a lot. It covers only about one half of the southeastern United States. But a really important difference is shown here by the percentage of the cloud-to-ground strikes that are positive. Notice that even over the southeastern U.S., where most of the strikes there's a high density of lightning strikes, still more than 20% of the strikes are positive, and in some areas of the country, the northeastern U.S. and the west coast of the U.S., the percentages of the cloud-to-ground strikes that are positive gets up as high as 40 and 50%. And that's what we're going to be addressing in the following case studies. We're now going to be looking at 5 cold season examples, and during the live teletraining we ask a lot of questions during these examples to try to lead the forecasters into maybe some of the reasons why these high positive flash counts are found in the winter season. We'll be looking at a long loop from the southeast United States, and we'll be looking at a loop with a lot of positive strikes in it. From the Pacific coast, we'll be looking at a Midwest example to show that the high positive flash count occurs inland as well. And finally, we'll be looking at the one exception to the high positive flash counts, and that's lake effect snow. This loop illustrates an extratropical cyclone that came out of the southeastern United States and moved out into the Atlantic Ocean and then up the Atlantic coast into New England over a several-day period in March of 2001. The important thing here that we like to point out to the class is if you look at the flash count as registered by the AWIPS output here, let me stop the loop, you'll notice that in most portions of this loop we're looking at positive flash counts that are at least 15% and many times much more than 15% of the total flash count, of the total CG flash count. As we go through this loop, we begin to ask the forecasters questions like, why would this be the case? What's different in the winter versus the summer if all the general physics principles that we've learned in Lightning Met 1 still hold true? The answer, of course, that we're looking for is that during the wintertime, some of the answers we're looking for is that during the wintertime, shears are a little higher, so the advection of positive charge downwind in the anvil happens more quickly. There's a lot less cloud liquid water, so there's a lot more stratiform precip in which the convection is embedded, indicating a high count of positive CGs. And also cloud tops are closer to the ground because the tropopause is lower. So when we work through this loop with the class, we're asking a lot of questions, and that's generally the idea that we're trying to get across. The next example shows an extratropical cyclone that's moving off the Pacific into the Oregon-Washington area. It shows a couple of characteristics of Pacific coast storms, especially cold season storms, very clearly, namely the low CG flash count, low total CG flash count, and the fact that when the strikes do occur, they're mostly positive, and that holds true along most of the Pacific coast. And in fact, if we look at a second example where we just look at an hour's worth of lightning from a storm that was producing a lot of cloud-to-ground lightning, we'll see that the high positive flash count holds true even for those type of storms. And here is that example, 10 to 12Z on the 2nd of December 2001. Notice we have a very high flash count, especially for the cold season. It's an unusual storm. We have about 236 flashes in a 1-hour period, and notice that about 90% of them are positive. Next, we look at an example over the midwestern U.S., a low-pressure system tracking up from Iowa through western Wisconsin into Canada. And again, we point out to the students the high number or the high percentage of positive flashes, again illustrating the principle we've been talking about through this whole part of the session here. And finally, we look at the one exception to the high positive flash count during the cold season, the lake effect snow event. At this point, we try to pick an office that is close to the Great Lakes. And if we can't find an office that's close to the Great Lakes, then we just ask any office to answer kind of randomly why this would be, why we would have very low percentage positive during lake effect snow convection. The answer that we're basically looking for is lake effect snow boundary layer is very warm and very moist comparatively compared to the rest of the continent. The lakes are fairly warm and the boundary layer is fairly moist. And there's a lot of graupel in lake effect snows, oftentimes, particularly the heavier events. Cities like Buffalo frequently report heavy graupel or a lot of dendritic activity. And during those periods, the lightning, the cloud-to-ground lightning, is generally negative. Now, summarizing the examples we just looked at for that south central and southeast lightning example that we showed for the time of that entire loop, you can see that nearly 20% of the CG lightning was positive. In the Pacific Coast cases we looked at, 80 to 90% of the lightning was positive, and for the Midwest case, about 40%. The Great Lakes case here and others that we've looked at, 0% positive, particularly if the Great Lakes, particularly if the lake effect snow event is intense and involves graupel. And remember the reasons that we gave, the three primary reasons for the cold season convection to have a higher positive cloud-to-ground flash count. Reason number one, the storm tops are lower, so the anvils are closer to the ground. Number two, vertical wind shear is greater, so these positive charges can infect a lot further downwind. And finally, cloud liquid water is less, which favors the inverted charge structure that we talked about in Lightning Met 1. So in summary, cold and warm season lightning are similar in most ways. Negative CGs are associated with the convective precipitation in both seasons, and the positive CGs are generally associated with anvils and stratiform precip regions. But lightning climatology does indicate important differences, namely, the total flash densities are lower during the cold season, no surprise, but also that the percentage of positive strikes are greater during the cold season. This is the norm for the cold season. We'll be getting to a section later for warm season severe storms where a high positive flash count is significant, but during the cold season, a high positive flash count is normal.
The objective of Section 4 is to see why severe NSD storms may exhibit unusually high and variable CG flash rates. To do this, we'll talk about the updraft behavior within the severe storms, and we'll talk about the CG flash rate and percent positive CGs within these vigorous updrafts, including some theory and some research results. And John will then do a case study from Birmingham, Alabama from 8 April of 1998. I'll start with a couple of research results. The first is from Foot and Frank in 83 and Burgess and Lemon in 1990. They found that severe and tornadic thunderstorms often pulse in intensity over a 15 to 25 minute time period. Knapp in 94 found that severe and tornadic thunderstorms often have unusually high flash rates that can vary periodically. This is a figure from the Foot and Frank paper in 1983, and what we're looking at are three different types of storms: the multicell supercell hybrid, and then the supercell. And as you go down here, we're going forward in time for about 15 to 25 minutes. For the multicell, you can see that the cell actually pulses in intensity as the new cores merge with the main cell. Here at the beginning, we have a fairly strong updraft. As the new cores merge, the updrafts are much weaker, and then we again have the strong updraft at the end. For the hybrid, the supercell multicell hybrid, it's a similar thing, except the transition is a little bit more rapid, where we have a very strong updraft, the merging occurs, and then again we have the strong updraft at the end. For a supercell, they pulse in intensity as the compact feeder cells on the flanking line merge with the main cell. You can see at the beginning here we have an intense updraft. As the feeder cells merge in, then it may weaken just a bit, and by the end here we're back to a very strong updraft again. So what about the CG flash rate? Well, the CG flash rate tends to increase as an updraft strengthens for this reason. If we increase the updraft within a supercell, or within any storm, we are therefore condensing water at a much greater rate. If we condense water at a greater rate, we have more supercooled droplets available for graupel formation. Therefore, we produce graupel at a much greater rate and increase the number of collisions between the graupel and ice. What happens when we increase the collisions? Well, we have more and more negative charge now associated with the mid-levels of the storm right in this area. So we call this enhanced charge, and this simply has to do with overall we're increasing the number of collisions between the graupel and ice. We have lots of graupel and therefore lots of negative charge. These are a couple of research results. The first is from Hawley and Meyer in '82, and this is a study of 380 minutes of non-severe Florida thunderstorms. Keep in mind now that these are non-severe. What we're looking at on the x-axis is the 1-minute CG flash rate, and on the y-axis would be the total number of occurrences, the total number of minutes. Notice that in almost all cases, we had less than about 3 CGs per minute, so a very low flash rate. Only in a couple of instances did we have 5 CGs per minute. So that's a fairly low flash rate. The other study was from Knapp in '94, where he was looking at negative flash-dominated severe storms, or NFD severe storms. And the key here is that these were all severe. And this is a much different picture. First of all, there were less minutes overall analyzed, but it doesn't really matter because notice in so many instances we had greater than 5 CGs per minute. And in one case we had as many as 20 CGs per minute. That actually may have happened twice here. What does that mean? Well, it means that we had 1 CG flash about every 3 seconds. So the point of this is to show that severe storms have a much, much higher flash rate than do non-severe storms. Now, in addition to this enhanced charge mechanism, we have something else going on. Let's say we have a supercell, and suddenly the updraft increases dramatically. So we have one of these pulses going on where the updraft strengthens dramatically. What does that do to these charge-carrying hydrometeors, these negatively charged graupel particles, and the positively charged ice crystals above? Well, what it would do would be to at least temporarily loft them further up into the storm. That takes the negative charge further away from the surface, which would actually tend to decrease the flash rate for these negative CGs, mainly because the negative charge is so far from the surface, discharge has a difficult time to occur. So this discussion suggests that we have a competition going on in these vigorous and evolving updrafts, which we find within supercells. We have an enhanced charge, which would increase the flash rate. At the same time, we may have some elevated charge associated with a strengthening updraft, which would actually decrease the flash rate. And this sort of suggests how we would see a pulsing activity within the lightning activity of a supercell. The following examples show the correlations between severe weather and pulses in the CG flash rates. This figure is from a paper by Kane in 1991, and is a case study from the central Massachusetts area on 2 June of '89. What we're looking at are the CG flash rates of a group of thunderstorms which moved through the area on this particular day. The flash rate is over here on the y-axis, and you can see overall throughout the state there was very high flash rates. And then we're looking at the time on the x-axis, or from about 1630 UTC up to about almost 22 UTC. So it's about a 4 or 5 hour time period. Several things to point out here. The first look at the black line. That would be the hourly CG flash rate. We see basically a steady increase and then a fairly steady decrease. In other words, it's not very jumpy. It's a fairly smooth line. So that's really not all that informative. All that really tells us is that the thunderstorm activity in general was increasing throughout most of this time period and then began to decrease around 2030 UTC. However, if we look at the 5-minute CG flash rate, it's much different. We see these pulses going on in the 5-minute data, 4 different distinct pulses. And now I'm going to toggle on the severe weather which was observed on this particular day, and you can see that we had several wind gusts greater than 60 knots, a large hail report, and some other significant weather which occurred. And this is plotted on the time scale as well, and the severe weather occurred after the beginning of this pulsing activity within the CG lightning data. As a second example from the same paper, we'll look at a case from South Central New York on 28 August of 1988. This is the same type plot, except now we're looking at a shorter time period, only about an hour and a half. Again, the hourly CG flash rate plotted here increases almost linearly throughout the period. But if you plot the 5-minute CG flash rate on top of that, you can see 2 distinct pulses which occur. And that's not evident whatsoever within the hourly flash rate because these pulses are averaged out. If we again toggle on the severe weather, you can see that there's quite a bit of severe activity which occurs after the pulsing goes on. Now the idea here is, what we're trying to get across is, look for this pulsing behavior in the 5-minute or the 15-minute CG lightning data. This is another thing that you can add to your list of severe storm parameters. I'm not saying you should warn or not warn based only on the 5-minute CG flash rate, but it's something else that you can look at in maybe a borderline severe situation. Now we're going to look at the effect that a supercell or a severe storm has on the percent positive CGs. Well, it turns out that the percent positive CGs may be elevated above 15% in severe NSD storms. A couple of reasons why this may be the case. The first is, within a severe storm, we generally have much greater shear values. So that means that the anvil will be advected downwind at a much greater rate, and we see these positively charged ice crystals advected down as well, and therefore we would see a greater likelihood of seeing some of these positive anvil strikes or positive strikes from the upper portions of the cloud. The second reason is because of this very strong updraft, we sometimes see the tilting of the updraft, and that's indicated here by this red line. What that does is allow some of these positively charged ice crystals located up around the minus 30 Celsius level to become unshielded and basically to move themselves out from over the negative charge, and we would expect the likelihood of seeing a positive CG coming out of that precipitation overhang. Now at this time I'm going to turn it back over to John, and he's going to talk about a case study from Birmingham, Alabama, which illustrates some of these points in the severe the severe NSD storms.
On the 8th of April 1998, the western suburbs of Birmingham, Alabama were hit by an F5 tornado. We're going to look at just a little bit of data from that case to show how lightning data follows some of the rules for severe negatively strike-dominated storms that Dan Lindsay was just talking about. Now, what we're looking at here is we're looking at a infrared channel 4 loop from goes east. Just a real quick setup here. The synoptics aren't all that important to the discussion that follows, but we do have a boundary here that stretches across central Alabama. As a shortwave moves in from the west, we have a tremendous line of convection that builds along that boundary. Winds aloft were very strong. We had a great deal of instability at low levels. The jet was as strong as 175 knots in the area, and this is a classical setup for severe over the southeastern United States. You'll notice that on the infrared satellite data, if we stop the loop here, we march along, looking at how these storms form up. We can see that very early on in the life cycle of the storm, we begin to see some cold tops poking up on the thunderstorm anvils. And later on in the loop, as we approach the Birmingham area, we see a very clearly well-defined enhanced V in this storm, where we did have an F5 tornado, and in this storm here, where we had 2.5-inch hail and some other overshooting tops, all associated with severe weather. We can toggle on the lightning data now. We don't advise looking at lightning data at this great a distance, but let's toggle it on and see what we can see. And as we step through the loop here, we can see one characteristic that jumps out immediately, namely the very high flash counts around those severe cores. This was a hail core here, this was a hail core here, and this was a tornadic core right here. We also have some high concentrations of lightning that are building up in these storms just across the border back in Mississippi, and they will become hail producers, that is, within the hour. But let's move in a little bit closer now and look at the particular storms that caused the problems for Birmingham. Now we're looking at the 0.5 degree tilt base reflectivity data from the Birmingham radar. And at this point in the session, we generally ask the students a couple of questions. I stop the loop and I ask the students to begin walking through the loop and describe what they see. This is Tuscaloosa County here. This is Jefferson County, in where Birmingham, Alabama is located. And of course, the first thing that the students notice is this supercell that's moving in from the west with this very well-defined hook echo that has a lot of continuity with time. But we try to elicit through questions how much continuity that hook echo really has. And if we go back to the beginning now and just walk along with that loop, we see at this point it's very well defined. It begins to lose a little definition here. Interestingly enough, there was an F2 tornado, I guess there was an F3 tornado on the ground that lifted off about the time that the hook echo was beginning to lose a little bit of its organization. And now the echo begins to get organized back into a real well-defined hook, and the F5 tornado touches down. As the storm passes through the western suburbs of Birmingham and then on out toward the east, it begins to lose definition again. And so we can see this little pulsing behavior that Dan talked about. Now if we toggle on the CG lightning for this same loop and just walk through it, there's a lot of things that jump out at us again immediately, and that is the high concentration of CG lightning associated with the storm that's headed toward Birmingham. Not only does it have a high concentration, but if you'll pay attention to the positive or to the total flash count up here at the top of the screen, you'll see that total flash count begins to vary quite dramatically, getting higher and higher and higher with time. Here we've got almost, and these by the way are 5-minute strike counts here, so that's a lot of strikes. It's also picking up some storms up here to the north, but most of it is in this storm right here. And as we move along, you'll see the total flash count then decreases and then begins to increase again as we get past Birmingham. We'll next look at a graph that plots this lightning flash count for the Birmingham storm alone. But before we do that, we're going to look at we're going to try to isolate in on the Birmingham storm using the greatest zoom we can do on the AWIPS. So zooming in once again on the storm that's going to hit Birmingham, we again see these characteristics, and the reason that I wanted to zoom in to this last step here is to show that when we're just looking at primarily the Birmingham storm, you can definitely see the pulsation in the total lightning count. We begin with 50 strikes over this 5-minute period, and as we go along here, we increase to where we have well over 100, and in fact we get over 200 as the storm moves past Tuscaloosa. Now what we're looking at is a time cross-section of various facets of the Birmingham storm, beginning at 22:30 and going on through 03. And the first thing you might notice about this graph is the increase in lightning flash rate, the general increase in lightning flash rate with time. We go from 0 to, say, on average, all the way up to 140 counts over a 5-minute period. Another thing that you should notice, since we've talked about it, is the pulsing behavior, which begins here around 23:15 or so, and you see a little pulse develop here. And we're not trying to make a one-to-one correlation with tornadic activity or with hail activity, but rather to show you and to illustrate the fact that the pulsing behavior that the updraft exhibits in a supercell storm is often mimicked by or reflected in the total lightning count. And once again, you can see this pulsing behavior. It's quite important here. These are the tornadoes that happen. This is an F3 tornado. Here's the F5 tornado. Touchdown first at 0045. And finally, as the storm moves out of Alabama, we got a small F2 tornado. So the storm continued to produce severe weather, and the updraft intensity continued to pulse, as did the lightning activity. If we toggle on the percent positive, we plotted the percent positive here in black, and you can see that for much of the storm's lifetime, particularly when it was severe, the total positive flash count went up over that magic 15% mark. In fact, for just a very short period, it went up over 50% here. But in general, this was a negatively strike-dominated storm with a very high flash count and a very high an unusually high percentage of positives. And we strongly suggest that if you see a storm that has a high percent positive flash count, and it has a fairly intense echo, that you treat it as a potentially severe storm. So in summary, for the severe negatively strike-dominated storms, it's been shown that the negatively strike-dominated severe storms are similar to typical warm season thunderstorms in that the negative CGs are associated with convective precipitation and grapple formation. The positive CGs are associated with the upper levels and with the thunderstorm anvils. The thing that sets the severe NSD storms apart is that the NSD storm exhibits unusually high and variable CG flash rates, and throughout much of its lifetime, the percentage of positive CGs is above 15%, but generally below 50% for the total storm count. The CG flash rates can be explained by a competition between the enhanced charging, and then the elevated charge as the storm pulses. And the percent positives, the elevated percent positives, may be due to the lifting of the updraft and the stronger shears. Some of those positively charged particles getting pushed out into the overhang.
This is Dan Lindsay again. I'm going to now go to Section 5. The objective of Section 5 is to be familiar with the severe PSD storm, and we'll talk about some hypotheses used to explain these storms. We'll look at some climatology, talk about the role of moisture, and talk about some characteristics of severe PSD storms. And then John will do a couple of case studies from North Platte, Nebraska, and Norman, Oklahoma. And finally, we'll also talk about the charging modes and charge distributions within the PSD storms. This map is from Carey and Rutledge in '99 and shows the density of hail and tornado reports averaged over the 1989 to 98 warm seasons. And what you can see is that we have a maximum of severe weather located in the central part of the country, exactly where you may expect, extending from northern Texas throughout Oklahoma and Kansas and into northeastern Colorado. So the question may arise, what percentage of these reports are PSD based on CG lightning during the hour around severe weather? Well, this graph shows the answer. What we're looking at is the percent of hail and tornado reports associated with PSD storms. Notice the color coding first. Yellows here indicate over 50% of hail and tornado reports are associated with the positive strike-dominated storms. And also notice the area of the country. This is no coincidence. This is the same area of the country where we saw lots of positive strikes in the lightning climatology earlier, from western Minnesota, southwestward, through Nebraska, and into northeastern Colorado. This is actually quite significant. If you look in northeastern Nebraska, you can see that over 70% of hail and tornado reports are associated with PSD storms. This figure is from Smith et al. In 2000, and there are several different things plotted here, so I'll take a minute to explain. The first are the brown lines here, and these are contours of surface theta E values. And you can see what we're looking at is a map of Oklahoma here and Kansas here, and we have a surface theta E ridge which extends north-south up through central Kansas and central Oklahoma. The second thing plotted are these, I guess, red lines which extend from the southwest to the northeast, and these are storm tracks from this day, 26 April of 1991, and the storms are actually given these different letters. This would be Storm K, Storm W, etc. And the final thing plotted on here are the CG lightning strikes. The red lines are the positive strikes, and the red dots are the positive strikes, and the blue dots are the negative strikes. So what Smith et al. Found is they looked at a correlation between where the storms formed in relation to the surface theta E ridge and whether they tended to be NSD or PSD. Let's, for example, look at Storm K. It forms here on the western side of the theta E ridge within the high theta E gradient. Moves to the northeast, and at its onset you can see almost entirely positive strikes. So this is a PSD storm. As it moves to the eastern side of the ridge, it actually switches over around this point and becomes an NSD storm. Almost every single storm on this particular day experiences or exhibits similar behavior. Storm C, for example, forms in the same area, is a PSD storm, moves over to the northeast, and becomes NSD. Storm O is an exception, but it's not really an exception because it forms within the middle of the theta E ridge rather than being on the dry side of it. And it's actually an NSD storm throughout its life cycle. Here's another study from the same paper. This is 13 March of 1990, and again, now theta E is contoured in black solid lines, and you can see that the theta E ridge extends northward through central Oklahoma and then northwestward into central Kansas. And again, we have the storms plotted. Storm H here is an example, forms on the western side of the theta E ridge, is a PSD storm, moves off across the ridge into the drier side of the ridge, and switches over to be an NSD storm. And here's an example, again, of storms which form within the theta E ridge itself, and they actually are producing negative strikes throughout. So Smith et al. Came up with a conceptual model based on these results. This is the model. We have three different storms indicated by A, B, and C, and we have colored here the surface theta E values with a ridge located here. Storm A forms on the western side of the ridge within the high theta E gradient, is a PSD storm indicated by this positive sign, moves to the east, and then transitions to an NSD storm after it crosses the ridge axis. Storm B, on the other hand, forms in the same area, is a PSD storm, but it doesn't cross the ridge. It remains on the dry side of the ridge, without crossing the high values of theta E and remains a PSD storm throughout. And finally, storm C forms on the eastern side of the ridge, where the gradient is much less, and it's a negative strike-dominated storm throughout its life cycle. Now we can talk about some characteristics of these severe PSD storms. First of all, severe PSD storms are loosely defined as storms dominated in the core by positive CGs for a significant part of the mature phase. PSD storms with appreciable positive CG flash rates, that would be positive CG flash rates greater than about 1.5 per minute, usually produce hail and sometimes produce tornadoes. Long track tornadoes and F5 damage ratings are often associated with these severe PSD storms. Also, severe PSD storms are often associated with severe thunderstorm outbreaks and low precipitation or classic supercells. So LP or classic supercells, generally no high precipitation supercells. HP supercells tend to be NSD. Severe PSD storms usually transition to NSD at some point during their lifetime, and this transition is usually marked by severe weather and oftentimes the LP or classic supercell to the HP supercell transition. Now at this time I'm going to turn it back over to John, and he's going to look at a couple of case studies, the first from North Platte, Nebraska.
Okay, this first example is from the 24th of July, 2000. What we're showing here actually is the ADA 12-hour forecast valid at 0Z on the 25th. We see a ridge running from northeastern South Dakota down through central Nebraska and on into western Kansas. Flow aloft on this day was northwesterly, and we'll show the sounding in a minute. We had a great deal of air mass instability, so we're basically expecting a severe weather outbreak with any supercells that form to maybe move to the right. And indeed what happens is the theta E axis and the flow aloft, along with the storm dynamics, play a role in putting the severe weather right down through central Nebraska. These are the SPC reports for the 24th of July, and you can see that the severe storm reports pretty much followed that theta E ridge right from northeastern South Dakota on into central Nebraska. Here's the sounding for that day. It was a little dry in the low levels in the early morning hours, but as the day progressed, the air mass got a little bit more moist, a little bit further in depth, and this is a parcel based on afternoon conditions near central Nebraska, and you can see that there was a great deal of instability and a great deal of wind shear. We'll talk a little bit later about what role this dry layer aloft may play in making this a PSD storm, and give you a couple of conflicting theories on that. At this point in the live session, we again show a radar loop, and we stop the loop and ask a forecaster from some office to step through the loop and describe this storm. We're looking at 0.5 degree base reflectivity. This is this border here is the South Dakota-Nebraska border, and this is the storm we'll be looking at. That's the storm we'll be directing our questions at. And what we're hoping that the forecaster notices is first, the storm itself splits very early in its lifetime, which is one sign of a severe storm. You can see it splitting right there. We also hope that they notice, and if they don't, we bring up the point ourselves, that there's this flying V signature in the reflectivity. We're quite a distance away from the KLNX radar there at Thetford, Nebraska. And as we go along here, we begin to see activity. We begin to see some pretty tall towers forming on the southwest flank of the storm. I say tall towers because we're still nearly 100 nautical miles away from the storm, and we're beginning to see reflectivities. And we hope that the forecaster recognizes that that may be a thunderstorm outflow in which discontinuous propagation is taking place. Continuing through the loop here, you'll see more and more activity around the flank. As the storm crosses into Nebraska, we begin to see lower and lower into the storm, and as we do, we begin to see a nice hook echo associated with the updraft. And most forecasters by this time will say, yes, we do expect tornadoes with this. Well, actually, the first tornado touched down up here, and the second tornado touched down here. There was very large hail throughout this portion of the path here and throughout this portion of the path here. So in this case, there was sufficient information from the radar, and I didn't even show the velocity, but the velocity was very helpful in identifying the mesocyclone associated with the storm. That plus the synoptic and mesoscale data were enough to show that this storm here needed to have warnings. But let's toggle on the lightning data and talk about some value added here. As we go along with the storm here, stepping through now with the lightning toggled on and watching just this core, we begin to notice two things. First, notice the negative strikes out here in the anvil region. And second, notice the very low flash count associated with that thunderstorm core. And when we do see flashes, they become positive. Now, this is a classical PSD storm for the area that we've been pointing out in the north central plains. They do happen in other regions of the country, but they're very predominant here. When you see that signature, you can pretty well guess that you're looking at a severe storm, at least a hail producer, and with good circulations in the storm, probably a tornadic storm. And so we now see the total lightning flash count here is also pulsing somewhat. Watch the positive counts as we come into Nebraska, get to the time of the second tornado right about here. And we see very low flash counts for 5-minute periods. To get a little better look at the lightning associated with the core of that storm, we now look at the composite reflectivity so we can zoom in on the storm just a little bit more and step through the loop again and pointing out that the core in this case is almost completely dominated by positive strikes and the anvil is dominated by negatives. This is a characteristic PSD storm, positives in the core and negatives aloft, and we'll be discussing in a minute the reason for some of the conflicting reasons for why this may be occurring. But you can see clearly that we do have that characteristic positively strike-dominated core. Here's another time cross-section similar to what we looked at with the Birmingham case. And you can see that as in the Birmingham case, the total lightning count increases with time, but one thing to notice here with a PSD storm, notice that the lightning flash count is much, much lower than it was with the severe NSD kind of storm. And I'll toggle on the positive counts in the following way. Let me describe this a little bit. Also notice the pulsing behavior of the lightning, of the total flash count of lightning right here. Let me erase that and describe what we're looking at here with these little diamonds. The magenta-colored diamonds here represent the percentage of positives during these various times, the percentage of positive strikes within the core, and you can note, and you'll see here that throughout most of the lifetime of the storm, nearly 100% or 100% of the strikes in the core are positive, and none of the strikes in the core or in the anvil are positive. In other words, all the strikes in the anvil are negative. So we have basically a reverse charge structure here, and that continues throughout most of the lifetime of the storm. There is never a time when the positive flash count, there's only a couple of times, I take that back. There's 3 5-minute periods here when the positive flash count drops below 50, but for the vast majority of the time shown here, we have a high positive flash count, higher in fact than 75 for most of the time. Okay, so moving from the 24th of July case here, we'll now look at an area of the country that maybe isn't quite so dominated by PSD storms. We're going to look at the famous 3 May 1999 case study. This is the ADA analysis from the late afternoon of 3 May, 00 on the 4th, which local time is around 18Z. We see a Theta ridge stretching down through central Oklahoma. We next use the MSAS data to zero in on central Oklahoma and look at some hourly analysis of the surface-based Theta E, shown in colors here, overlaid with the CG lightning data. And as we walk slowly through this loop with time, we can see that most of the cores, they're a little hard to see, but most of the cores are PSD. The pretty open areas here are the negatively strike-dominated areas, and in this case, that's an anvil right there. There are some negative strikes here that are difficult to see, but they are negative. But notice the total count. Notice the total lightning count here. Keep track of that as we walk through this loop. And you can see that most of the storms have a very high positive count. The anvils themselves have very low counts, similar to the case of the normally charged storms, the negatively strike-dominated storms. The anvil strikes are much lower than the total number of counts within the core. In this case, we get 40% of the 40 to 50% of the strikes are positively strike dominated, are positive strikes, and they are associated with the thunderstorm cores until the squall line fills in and moves east of that surface theta E ridge, and then suddenly we find a very high negative count. So even on the 3 May day, that principle, the principle of the positive strike dominated storm held true. As the storms crossed the theta E ridge, they became NSD. Here's a close-in view of base reflectivity for the Moore storm with the lightning data overlaid, and you can clearly see here that the storm was definitely positively strike dominated, and that was the characteristics for most of the storms in western and central Oklahoma before they crossed the theta E ridge. Now let's talk about why these positively strike dominated storms may be the way they are. There are a number of theories about this. We're right at the edge of research here, and not too much is really known about them. I'll describe a couple of the theories. Remember that in a typical NSD storm, the high cloud liquid water in the updraft kind of dominates the situation in terms of charged grapple and the collisional process between charged grapple that has a very wet skin colliding with small ice particles that take on the positive charge and are then evected up into the anvil and then downwind. In the severe PSD storm, research results indicate an inverted charge structure where the grapple area of the storm is positive, indicating that the grapple has taken on a positive charge and that the smaller particles have taken on a negative charge. A couple of ways this can happen. A lot of research, beginning as far back as Takahashi, shows that if grapple is forming in a less than normally high cloud liquid environment, in other words, if there's enough moisture to form grapple but not enough to keep a thick wet skin on the grapple, sometimes the grapple will charge positive. One of the things that's being looked at now from a research sense is that in a severe thunderstorm, oftentimes on the high plains, particularly on the western high plains in a dryline situation, we get a rear flank downdraft develop, and research by Eric Rasmussen, Paul Markowski, and others have shown that these rear flank downdrafts are very, very dry. They're forced to the surface as very dry air, but they are actually positively buoyant with respect to the inflow air, and so a lot of the dry air can get wrapped back into the updraft. So on the west side of the updraft, near the rear flank downdraft, we have a fairly dry updraft, relatively dry compared to the eastern side of the updraft. Now, if and when that occurs, and this grapple being heavier begins to drop down from aloft into that drier portion of the updraft for recycling, it will lose its thick wet skin and become dry, and the collisions that occur there can produce negatively charged ice crystals. That's one theory. I think it's the favored theory right now, but there's no proof that that's actually true, but it makes a lot of sense relative to previous research that's been done. Meanwhile, it's also been shown that extremely high cloud liquid water environments, that's very high cloud liquid water environments, can also charge grapple positive, and nobody knows why that is. In fact, grapple in an extremely high cloud liquid water environment is almost like a raindrop. So collisions that are happening between that and ice are probably quite different than those that are happening between grapple with just a thin water skin. But for whatever reason, this is what for whatever reason it occurs, and I'm sure the lightning people are going to figure that out shortly. For whatever reason it occurs, this is a typical charge structure within a PSD storm. Positive in the mid-levels, whereas the typical storm has negatives in the mid-levels, with negatively charged ice crystals ejecting down into the anvil and a small negative layer here near the 0 sea level. So in summary, severe PSD storms are anomalous. They're the real anomaly compared to all the other storms that occur across the U.S. They are positively strike dominated in the storm core in the grapple areas and negatively strike dominated in the anvil. There are oftentimes PSD and NSD reversals during the mature phase, and there is little to no lightning for extended periods for PSD storms. The CG strike locations are consistent with inverted charge structure, with the inverted charge structure that I just showed, And one thing we want to drive home is that the geography of PSD-NSD storms appears to be linked to the surface moisture distribution, though what that has to do with moisture in the vertical is still up for grabs. I want to point out that PSD storms can occur in other parts of the country. When they do, they're dangerous. I also want to say that research has shown that storms with a high positive count, even though they're not positively strike dominated and even though the positive strikes are not occurring in the core, are also storms to be watched. Low CG production may be caused also by an elevated charge. That may be the reason for this little to no CGs for extended periods.
Now, going through a few conclusions of the Lightning Meteorology 2 session, first we talked about typical warm season storms, and we found that they usually produce less than 15% positive CGs over their life cycle. These typical warm season storms tend to be negative strike dominated, but they may transition to PSD storms during dissipation. As far as the CG lightning, we expect to see negative CGs associated with the convective precipitation, and primarily positive CGs associated with the anvils and stratiform precipitation. As far as cold season lightning, we see similarities with typical storms in that the CG production is the same with respect to the storm regions. However, there are some differences. We see lower CG flash densities overall, and we see a higher percent positive CGs, oftentimes greater than 15% and sometimes greater than about 50%, especially along the west coast of the U.S. So the forecaster alert here is to expect lower flash densities and higher percent positive CGs in most cold season scenarios. As far as severe NSD storms, again, the CG production is the same with respect to the storm region as the typical storms. But within these severe storms, we see unusually high and variable CG flash rates. In addition, the percent positive CGs tends to also be greater than 15%, but by definition is less than 50%. So the forecaster alert here is that unusually high and variable CG flash rates should be added to the list of severe storm signatures, and elevated percent positive CGs may be observed in some of these severe NSD storms. For severe PSD storms, we see many differences from the typical storm. The storms are positive strike dominated within the core and negative strike dominated within the anvil. We oftentimes see PSD to NSD reversals during the mature phase, and sometimes little to no CGs for extended periods, which is probably associated with a pulsing updraft. So the forecaster alert here is generally look upstream of surface theta E ridges in the central U.S. for severe PSD storms, although if you see positive strikes with a storm anywhere in the U.S., you need to pay particular attention to it because these are found to be associated with severe weather. Also, look for dense clusters of positive CGs within the storm core, and this should be added to the list of severe storm signatures. Now, before we conclude, I want to show you a website which is available to all addresses from NOAA.gov, so all forecast offices should be able to access this. This is the web address here, and these are lightning climatology maps which were produced by the folks at Texas A&M, including Dick Orville. If you go to this website, you'll see the map here, and you can choose your forecast area just by clicking on the particular city wherever you are. For the example I'm going to show, I'll do Denver. If you click on Denver, then it will move to the next page, which is here. And you have three choices. You can either choose the flash density, the positive flash density, or the percent positive. I'm going to look at two. First, I'll do the flash density and then the percent positive. So if I click on flash density, I get this. And this is the Denver forecast area, and you can see a very huge geographical variation in flash density in the Denver forecast area. You see very high values, greater than about 3.5 flashes per square kilometer per year, down here on the south side of Denver, and this actually is associated with a terrain feature called the Palmer Lake Divide. It's elevated terrain. So it's not too big a surprise for those living in the Denver area that we see more lightning down here than somewhere else. As the second example, if you were to click on the percent positives, we see a much different picture. We see the percent positives being much, much higher out on the northeastern plains of Colorado and throughout eastern Colorado, as well as in the Fort Collins area, than we do anywhere else throughout the forecast area in the mountains or down here on the Palmer Lake Divide. So the idea here is go take a look at your forecast area and see what you can see as far as the lightning climatology and the percent positives. So that concludes the Lightning Met 2 session.